Hi all, today we'll discuss about an important concept called locality of reference. So the locality of reference. So the locality of reference it's one kind of phenomenon in which the computer program tends to access same set of memory locations for a particular time period. In other words, locality of reference refers to the tendency of the computer program. It is a tendency of a computer program to access instructions whose addresses are near near to one another. The property of locality of reference is mainly shown by loops and subroutine calls in the program. So let us discuss the concept called locality of reference. Locality of reference. That means in general when your processor, it is combination of CU and ALU plus some registers, refers issues an address that you may call virtual address in case of virtual memory. This has to be mapped to physical memory. This is virtual address 1. Next time when you issues virtual address 2, there is a tendency that virtual address 2 is near to virtual address 1. So there is a tendency that the virtual address 1 and virtual address 2 both are nearby. Nearby in the sense they are at very they are stored in the physical memory, that is main memory, very nearby. That means maybe consecutive address locations. And the best example for this rule, locality of reference, then we should get a doubt why we are stressing upon so much about this locality of reference. So now we understand what is meant by locality of reference. Let's understand some examples, then we understand why is the importance of this locality of reference. So uh, let me take some example. See, in case of simple C programming language, see the locality of example for locality of reference is, first one is loops, and next one is subroutine calls. So these are the examples of locality of reference. So why loops and subroutine calls are called locality of reference means, let's take one loop and try to understand the importance of locality of reference. So if this is my for loop, for I is equals to 0, I'm taking a for loop in C programming language, I less than or is equals to 10, I plus plus. So I is equals to I plus 1 and printf percentile d I. So in this case, what's happening in C programming language, this is a simple for loop in which I took a variable I initialized to which is initialized to 0 and which is incremented by 2 and then print the value. Let's take another value j is equals 0, j is equals to j plus 1 and print j. So this the body of the loop has two statements. One is j is equals to j plus 1, another is print j. So these two statements, can you guess how many times these two statements has to be executed? Yes, of course, it is 10 times because the for loop iterates starting from I value 0 to 9, no, 0 to 10, because I said I less than or equals to 10. So a total of 0 to 10 means 11 iterations. So for 11 times these two statements will get execute. So if you keep these instructions in a special memory, then it is very useful. So the goal is these looping, the body of the loop should be, we know that the body of the loop, that is these two statements will execute, has to be executed for 11 times. So is there any scope each time these instructions are stored in the physical memory, and each time you need to perform a fetch, you know about execution cycle: fetch, decode, execute and store. You need to perform this is called instruction cycle, and you have to do it for 11 times. See, as you know that these two statements, body of the loop, for loop in this case two statements at any cost has to be executed for 11 times, then why don't you make use of this concept, this work, to reduce the execution time of those instructions? Anyway, you know that 11 times the body of the for loop has to be executed. But the thing is, each time, and you know that if the body of the loop is stored in the physical memory, each time you need to perform the memory read operation, and it is a time consuming process. So if you keep these body of the loop somewhere near the processor and not in the physical memory, not in the register, but uh, why can't we, you should get a doubt, why can't we store those instructions in the register means? Registers are very limited in number wise and also the storage location wise. They can store at the max 32-bit registers or 64-bit register data. And the thing is, they cannot, their storage, the storage capacity of the register is very limited. You can't store 10 statements. So the body of the for loop may have 10 or 20 statements. So in this case, for simplicity, for simple understanding, I took two statements. I just mentioned two statements in the body of the loop, but that may not be the case always, right? There can be some 10 or 20 statements might need to be present in the body of the loop. Then registers are not advisable to store the body of the loop. So the registers are very nearby to processor. It would have been very advantageous if you store those in the register, but because of their limitation like storage capacity and their limited availability, limited number of registers, it is not advisable. And if you store in the main memory, physical memory, they are taking very long time. Each time you need to perform memory read operation and memory write operation. So there is a requirement to store those instructions in such a way that that memory should be fast and it should be near to processor. The goal is to reduce the execution time of the instructions. For that we are making utilizing a concept called locality of reference. So the locality of reference, what it says that the locality of reference, I hope you are getting now. So the goal of the locality of reference is that execution time should be reduced. Now let's understand this picture. See, all of you know that there is a secondary memory which stores the programs or all the instructions, and from secondary memory that will go to main memory, and from main memory in general it goes to CPU, processor. CPU means processor, which contains cache registers. And see a new word called cache. So I said right, there is a requirement for the instructions which you know that which you refer in near future very frequently, then it is not advisable to be present those instructions in the main memory. Rather than they should keep in a special type of memory. That memory should have two features. It should be near to processor and it should have some larger capacity than registers. So that memory is called cache memory. So the cache memory works on the principle of the locality of reference. The cache is designed solely to implement the concept called locality of reference. So the locality of reference means the computer program to access instructions whose addresses are near one another. The property of locality of reference is mainly shown in loops. Just now we discussed about loop, how the locality of reference concept can be implemented for loop. Similarly, for subroutine calls. For subroutine calls, what happens? You know that once you make a call to a subroutine means it's a function. When you make a call to a subroutine, you know that anyway the content, the subroutine has to be executed. So why can't you keep that subroutine in the cache memory? Then it reduces the cache memory. Having cache memory in a computer reduces the execution time. So the cache memory is used to store body of the loop or complete subroutine or function. Body of the loop or subroutine and function. So this is about the concept called locality of reference. So in case of loops, the control processing unit repeatedly refers to the set of instructions that constitute the loop. Just now we discussed. In case of subroutine calls, every time set of instructions are fetched from memory. So instead of fetching those instructions from memory, keep all those subroutine instructions in cache memory. And remember, if you are implementing a technique called recursion, recursion means a function or a subroutine calling itself. So a function which calls itself is called subroutine. So you don't know how many times uh, a function calls itself. So in this case, the cache memory is very useful, having cache memory. But how it works means, here you can say CPU means processor. When processor has, if the cache is present, cache memory is present, if the processor issues an address, then there are two options. Either it can act, first it can access cache memory to see whether this particular address is present in the cache, so that it need not to go to main memory. It is available in the cache itself. And you know that the advantage of having this instruction in the cache memory is that it can be accessed very fast, because it's very fast compared to main memory. So in the first attempt, what happens, it will verify whether the particular word is present in the cache. If so, there comes two possibilities. One, yes, the word is the required memory word or instruction or data is present in the cache itself. Then this is called cache hit. This is called cache hit. So the cache is a memory. Why we are discussing about cache in locality of reference means, yes, locality of reference is a phenomenon, is a rule which can be implemented by cache. So the cache is designed solely to implement the concept called locality of reference. So the locality of reference, this is called cache hit. Cache hit means processor first it will verify whether, yeah, whether the particular address is available in the cache itself. If it is available, it is called cache hit. If it is not found, so it will make a call to physical memory. It will try to search. This situation was called cache miss. So these are important words: cache hit and cache miss. So the references to data items also get localized, means same data item is referenced again and again. So this is about cache hit and cache miss. If you remember, if that particular word is not available in physical memory as well, this is called page fault. If it is not available in cache, it is called cache miss. So Next, see in the previous figure, we can see that CPU wants to read or fetch the data or instruction. First, it will access the cache memory. Why? Because it is near to it and provides a very fast access. If the required data or instruction is found, it will be fetched. This situation is known as cache hit. But if the required data or instruction is not found in the cache memory, then this situation is known as a cache miss. Now the main memory will be searched for the required data in case of cache miss that was being searched, and if you found, go through one of the two ways. Okay, let's assume the data is available in main memory, but it is not available in cache. So first way is that CPU should fetch the required data or instruction and use it, and that's it. But what when the same data or instruction is required again? Then the CPU again has to access the same main memory location, and we already know that main memory is slowest to access when you compare with cache. So in case of cache miss, what happens? It will just verify the particular memory location. So in case of cache miss, it will see that the word is available in the memory, and and in the next time if you try to, if the case may be that next time you may be accessing the same word or instruction, then again you need to go to directly main memory anyway, because that word is not available. Word is so in case of subroutine calls, every time the set of instructions are fetched from memory, so the references to these data items also get localized. So you know that if the required data or instruction is found, it will be fetched. This situation is known as the cache hit. But if the required data or instruction is not found in the cache memory, then this situation is known as cache miss. So how to deal with this cache miss? Now the main memory will be searched for the required data or instruction that was being searched, and if it found, will go through one of the two ways. The first way is that CPU should fetch the required data or instruction and use it, that and that's it. But when the same data or instruction is required again, the CPU again has to access the same main memory location for it, and we already know that the main memory is the slowest to access. Second way is to store the data and instructions in the cache memory, so that if it is needed soon again in the near future, it could be fetched in much faster way. Example is loop and subroutine calls. So the cache operation is based on the principle of locality of reference. There are two ways with which data or instruction is fetched from main memory. So there are two ways with which the data or instructions is fetched from main memory and get stored in the cache memory. These are the first one is The temporal locality. The temporal locality means the current data or instruction that is being fetched may be needed in near future or soon. So we should store the data or instruction in the cache memory so that we can avoid again searching in main memory for the same data. So what's happening here, if your processor is issuing an address and that particular word is not available in cache, this is called cache miss, that is available in physical memory, and bring that into cache and keep here, so that with an expectation that this address is again referenced in near future. This is called temporal locality of reference. So the temporal locality of reference means the current data or instruction that is being fetched may be needed soon. So we should store the data or instruction in cache memory so that we can avoid again searching in the main memory for the same data. So this is about temporal locality. So this is how the temporal locality works. Let's assume these are the main memory and these are the different locations, and this is the current memory location which CPU accessing. So the data stored in the cache tag memory and cache data memory with a tag. Remember, there is a tag, the cache. So when CPU access the current main memory location for reading the required data or instruction, it also gets stored in the cache memory, which is based on the fact that same data or instruction may be needed in near future. This is known as temporal locality. If the same data is referenced, then there is a high probability that it will be referenced again in a near future. This rule is called temporal locality. And there is a other principle which is called spatial locality. The spatial locality means the instruction or data near to the current memory location that is being fetched may be needed soon in near future. So let me explain. The spatial locality of reference says that if you are accessing a particular memory word in main memory, if you are referring address 1, then you may expect that you can refer address 2 and address 3 in near future. So please keep this in the cache memory. Address 2, address 3. This is called spatial locality of reference. I hope you are getting. Let me explain. If this is my main memory and it is divided into, let's assume, address, this is address 1, address 2, address 3 and address 4. The processor issuing currently address 1, and in the cache memory, if you store address 1 which is referenced recently, this is called temporal locality of reference. And in case of, if you store address 2, address 3, address 4, this is called spatial locality of reference. So the spatial locality reference means instructional data near to the current memory location that is being fetched may be needed soon in near future. This is slightly different from the temporal locality. Here we are talking about the nearly located memory locations, while in temporal locality we were talking about the actual memory locations that was being fetched. So this is about, so if you see the example here, this is my main memory. Presently CPU processor is accessing this particular memory location. Let's assume this is address 1, then this address 0, address 2, address 3, address 4. These are placed in the cache. This is called spatial locality of reference. So the locality of reference. Now we'll discuss something about cache memory. The temporal locality means programs tend to reference the same memory location at future point in time due to loops and iterations and programs spending a lot of time in one section of code. The best example for temporal locality of reference is that loops. You may execute the loops body of the loop for n number of iterations. So you'll be accessing the same set of addresses again and again. So it is better to keep those uh, loop body of the loop or function call body of the function in cache memory. Whereas spatial locality of reference, programs tend to reference memory locations that are near other recently referenced memory location. Due to uh, the way contiguous memory is referred, example an array. If you are referring an array element, first array element, then it is quite natural that you will be accessing the next array element. So the array key is a best example for spatial locality of reference. Locality of reference doesn't always hold, but it is usually holds. In general, it happens. Now we discuss about cache memory. The cache is a small amount of uh, fast memory. It sits between the main memory and CPU. May be located on CPU chip or module. See, sometimes the uh, CPU might be available within the processor itself. Internal, we call it as internal cache. If the cache is present within the chip of the processor, then it is called internal cache. If it is outside the chip of the processor, it is called external cache. So the entire blocks of data is copied from main memory to cache because the principle of locality tells us that once a byte is accessed, it is likely that the nearby data element will be needed soon. So the block means this block can be a body of the loop, or this block can be function body, or this can be an array. So you would transfer some block of memory to cache. So we'll discuss an overview of the cache operation. CPU requests the contents of the memory location First, CPU requests the contents of the memory location and check. First, it will see whether the particular data is available in the cache. If it is present, get from the cache. This is called cache hit. If it is not present, the read required block from the main memory. Main memory to cache. Then deliver from cache to CPU. Here CPU means processor. The cache includes tags to identify which block of main memory is in cache slot. So it uses a special technique called tag. Now we see some cache definitions, some basic definitions in the cache. A hit or a cache hit is when data is found at a given memory level. Miss means when the data is not available, not found in cache. The hit rate is the percentage of the time data is found at the cache. Miss rate, the percentage of the time is not available in the cache. So the relation between cache hit rate and miss rate is that miss rate is equals to 1 minus hit rate, or hit rate is equals to 1 minus miss rate. The hit time is the time required to access that data. The miss penalty is the time required to process a miss, including the time that it takes to replace a block of memory plus the time it takes to deliver the data to the processor. So the crucial thing is cache miss. Cache memory, the goal of the cache memory is that it should have less number of cache misses, or cache miss rate should be very low. So the miss rate should be very low, or hit rate can be very high. So these are the some basic definitions. We'll see some examples of the cache. Consider a level 1 cache capable of holding 1000 words. So let's assume a cache is capable of holding 1000 words with 0.1 microseconds of access time. Level 2 is a memory with 1 microseconds of access time. If 95% of the memory access is in the cache, then 0.95 times it takes 0.1 microseconds. 0.05 times takes first 0.1 plus 1 microsecond, because first you will refer the cache. If the 5% of the memory access in the cache, then this is the reverse. So we want as many cache hit is possible. So this is about some mathematical notation. This is very important notation from competitive exam point of view. Now let's see how a cache is designed. If a memory contains 2 power n addressable words, that means there are 2 power n possible addresses. The memory can broken into blocks with k words per block. So then If I have a physical memory or main memory where I can store 2 power n addresses, 0 to 2 power n minus 1 addresses, divide these 2 power n addresses by k. Here k is k words per block. So this is number of blocks. Now cache consists of C lines or slots, each consisting of k words. How to map the blocks of memory lines to cache? So these are blocks. Memory is containing blocks. You are saying line. So at any moment, one block or k words can be present in the cache. So there are how to design a cache memory, how to design its size, how to decide its size, what is the mapping function. Mapping function means which block is present in the cache, replacement algorithm, how to replace the cache blocks, write policy, block size, and how many caches. Cost. More, most of the caches are expensive. The speed of the cache is very faster. Up to a point, diminishing returns a cache increases in size. It also can take longer to search more cache. Suppose, let's see mapping function. Suppose we have the following configuration. Mapping function means, as I said, the physical memory is divided into blocks and cache can store 2 or 3 blocks. B1, B2, B3. So there should be a mapping. Suppose we have the following configuration. Word size is 1 byte. Cache is of 16 bytes. That means a cache can accommodate 16 words. So a cache can accommodate 16 words of 1 byte. Cache line or block size is 2 bytes. 2 bytes. So this is 2 bytes is 1 block. So 8 blocks. Cache can accommodate 8 blocks. So the cache line by block size is 2 bytes. That is, cache is having 8 blocks. So we need 8 addresses for a block in the cache. So first you should identify that 8, each block should have a number. So first it is required to address which block. Since the cache memory is accommodating 8 blocks, it needs 8 addresses. Main memory is of 64 bit. So 6 bits addresses needed for 64 bit. 64 bytes divided by 2 bytes, 32 memory blocks. 32 memory blocks to 8 lines in the cache. So these 32 bits can be represented using 5 bits. So out of these 6 bits, 5 bits are reserved to identify which block and 1 bit is to identify which word it is. So the 0 means first word in the block, 1 means second word in the block. That's it. This is the way of organizing the mapping function.